Hello, welcome back. In this lecture, I will introduce a little bit about this programming homework about solving a Hit equation using AD-semi and conduct inverse modeling. And yeah, if you look at the homework, you will see an equation like here. This is the Gavin equation, equation 1. And this is exactly the Hit equation we encountered in class in the AD section. And also we have specific boundary conditions, equation 2 and 3. And also in the first problem, you are going to solve a 1D Hit equation and estimate the parameters A and B in this kappa x, where kappa x is the thermal diffusivity coefficient here. And in the second problem, you are going to estimate this diffusivity coefficient kappa x without knowing the form of the kappa x, and you will use a neural network to approximate the kappa x, where x is the input to the neural network and the output is kappa x itself. And in the third homework, you are going to go do a 2D problem where your diffusivity coefficient is represented by a plus bx plus cy. And in this homework, you are going to use a custom operator, which is already coded for you, so you do not need to worry about the discretization form. And what you need to do is to plug this custom operator into the AD framework and conduct inverse modeling to estimate A, B, and C. So let's review a little bit about the Hit equation we encountered in class. And this is the mathematical optimization formulation of the Hit equation. Remember that this Hit equation, and this Hit equation is defined in 1D on a bar. And for this bar, for each point in the interior of this bar, it is described by a partial differential equation, which is exactly the Hit equation here. And on the left-hand side, you have the so-called insulated boundary conditions, which means that the Hit cannot go into the bar and the Hit cannot escape the bar. And on the right-hand side, you have directional boundary conditions, which means that the temperature is fixed. For example, you can use some machines here so that you pump the Hit into the bar so that the temperature is fixed. And in the first problem, we assume that the kappa is equal to A plus Bx, and A and B are unknown. What we can do is to place a thermometer here on the left-hand side and collect the temperature as time goes. And so you have a time series data. So like this, you have a time series, and you are going to estimate A and B from this time series. And the mathematical problem is actually pretty direct, and so you want to minimize your hypothetical temperature and your observation, U lot. And this is formulated as a PDE constraint optimization problem, where your objective function is the discrepancy between your hypothetical temperature and the actual temperature you observed. And the constraint is the PDE system, where the governing equation is the Hit equation, and you have the left boundaries and conditions and the red boundaries, and also you have initial conditions, which we assume is 0 everywhere. And kappa has this form: kappa x equal ax plus b. So let's see how we can put it into a computer program so we can solve this equation. The first thing to do is to discretize the equations. Like here, you want to discretize all the PDEs. So the idea is to here we use the finite difference. Let's see how we can discretize that. So the idea is that here we have a time derivative and also spatial derivative. We can use finite difference as we talked about in the first few slides in the AD lecture. We can use finite difference to approximate these derivatives. And this is pretty standard, and you can use finite difference to solve PDEs or finite volume or finite element, and they have some merits. For example, you can establish convergence and stability conditions for those kind of schemes. And actually, you also have a lot of sparse linear algebra libraries to solve the equation related to those kind of discretization. So this is the way we wish to go for. And here is the discretization for partial u, partial t. You can see this is just a forward difference where you use the next step minus the current step over delta t. And this is the discretization for Laplacian. Let's recall the Laplace u in 1D is just u prime prime. So yeah, this is the discretization for u prime prime. So actually the derivation is pretty simple. So you just take it to x prime xi plus 1/2 minus u prime xi minus 1/2, and this is over h. Okay, and then the next step is to discretize this term. And what's this term? This term is u prime x, not a prime, it's actually u x I plus 1 minus u x I over h. And likewise, you can discretize this term using u x I. Let me write somewhere else. Maybe just here, run out of space. Minus u x minus 1 over h. So you just put these two terms together. You remember you also have a h here, and so you get this. This h is exactly equal to delta x. So you get h squared in the denominator, and you get this term in the numerator. And you can also say that we use the superscript for time. So k plus 1 represents that this is at k plus 1 time step. Okay, let me erase everything here. So let's see how we deal with this 0k. Because 0k actually does not, 0k plus 1, the u0, actually does not exist in our set of variables. We only define u at this point, u1, u2, u3, and un plus 1. So this u0 is actually created from nothing. So the k for dealing with this u0 k plus 1 is that we either add this new variable into our original set of variables, or just eliminate them from our current equations. So let's go for the second way. Let's see how we can use this equation and eliminate some equations or some variables. Let's look at the governing equation at u1 at this location, at the leftmost set. So that corresponds to k equal 1. So let's write not k equal 1. That corresponds to I equal 1. So let's plug I into this equation. So we have uk plus 1 minus u1 delta t equal kappa 1 u2 k plus 1 plus 2 0 u0 k plus 1 minus 2 ui k plus 1. Oh, this should be 1, and delta t, delta x squared, and also plus f k plus 1, 1. Okay, so we already say let's use 0 here. So we do not want u0 to be our variable. So we want to eliminate that. How do we do that? Let's look at this equation. In this equation, we have u0k plus 1 is exactly equal to 2k plus 1. So we just plug it in, and these two terms is equal to 2k plus 1. So we eliminate u0, k plus 1, and modify the first governing equation, discretize the governing equation for this set of equations. Okay, alright. So we already solved this. We already tackled this boundary conditions. Next, we are going to deal with other conditions. For this equation, this is pretty easy. For this differential boundary conditions, you just set the rightmost variable to be 0, and that is shown here. That it is exactly here. And actually, this is k plus 1 if we are going to use implicit scheme. Okay, and what about the initial conditions? For initial conditions, already dealt with that. And for initial conditions, it's just like set for k equals 0, we set something like this. Okay, this is how we discretize the PDE. And this PDE is turned into a set of equations. And we can just write them into a matrix. We will have something like this. We'll have A times U k plus 1, where U is assembling everything together. And note we do not have U n plus 1, because we already know U0 n plus 1, U n plus 1 equals 0. So we can just eliminate them from the linear system. And this is just algebra, and then you also have the right hand side, and this is UK. You just assemble everything, write them into a linear system, and then you will get something like this. Okay, so for programming, you need to note that the coefficient here, this is 2 minus 2 lambda I, and the other coefficient is just lambda 2, lambda 3. Don't forget this too in your programming. Okay, and this is how you discretize your partial differential equation. And we will next we will think about how to program this partial differential equation, discretize the partial differential equation in Julian language.